Multi-leader replication topologies. A replication topology describes the communication path along which writes are propagated from one node to another. If you have two leaders, like in figure 5.7, there is only one plausible topology. Leader 1 must send all its writes to leader 2, and vice versa. With more than two leaders, various different topologies are possible. Some examples are illustrated in figure 5.8. The most general topology is all-to-all, in which every leader sends its write to every other leader. However, more restricted topologies are also used. For example, MySQL by default supports only a SQL topology, in which each node receives writes from one node and forward those writes, plus any write of its own, to one other node. Another popular topology has the shape of a star. One designated root node forwards writes to all the other nodes. The star topology can be generalized as a tree. In circular and star topologies, a write may need to pass through several nodes before it reaches all replicas. Therefore, nodes need to forward data changes they receive from other nodes. To prevent infinite replication loops, each node is given a unique identifier, and in the replication log, each write is tagged with the identifier of all the nodes it has passed through. When a node receives a data change that is tagged with its own identifier, the data change is ignored because the node knows what it has already been processed. A problem with circular and star topologies that is just one node fail, it can interrupt the flow of the replication message between other nodes, causing them to be unable to communicate until the node is fixed. The topology could be reconfigured to work around the failed node, but in most deployments, such reconfiguration will have to be done manually. The default tolerance of a more densely connected topology, such as all-to-all, is better because it allows messages to travel along different paths, avoiding a single point of failure. On the other hand, all-to-all topologies can have issues too. In particular, some network links may be faster than others due to network congestion, with the result that some replication matches may overtake others, as illustrated in Figure 5.9. In Figure 5.9, client A inserts a row into a table on leader 1, and client B updates that row on leader 3. However, leader 2 may receive the write in different order. It may first receive the update, which from its point of view is an update to a row that does not exist in the database, and only later receive the corresponding insert, which should have proceeded to the updated. This is a problem of causality, similarly to the one saw in consistent prefix reads on page 165. The updates depend on prior insert, so we need to make sure that all nodes process the insert first and then the update. Simply attaching a timestamp to every write is not sufficient because clocks cannot trust to be sufficient in sync to correctly order this event at leader 2. See chapter 8. To order these events correctly, a technique called version vector can be used, which will be discussed later in this chapter. See detecting concurrent write on page 184. However, complete detection techniques are poorly implemented in many multi-leader replication systems. For example, at the time of writing, PostgreSQL BDR does not provide causal ordering of writes, and Tungsten replication for MySQL doesn't even try to detect conflicts. If you are using a system with multi-leader replication, it's worth being aware of this issue. Carefully replication, the documentation, and thoroughly testing your database to ensure that it really does provide the guarantees you believe it to have. Leaderless replication. The replication approaches we have discussed so far in this chapter, single leaders and multi-leader replications, are based on the idea that the client sends a write request to one node, the leader, and the database system takes care of a copy that writes to the other replicas. A leader determines the order in which writes should be processed and follow apply the leader writes in the same order. Some data storage systems take a different approach, abandoning the concept of a leader and allowing any replica to directly accept writes from clients. Some of the earliest replicated data systems were leaderless, but the idea was mostly forgotten during the era of dominance of relational databases. It once again became a fashionable architecture for databases after Amazon used it for its own Dynamo system. Ria, Cassandra, and Voldemort are open source data store with leaderless replication model inspired by Dynamo. So this kind of database is also known as Dynamo Star. In some leaderless implementation, the client directly sends its write to several replicas, while in others, a coordination node does this on behalf of the client. However, unlike a leaders database, that coordinator does not enforce a particular ordering of write. As we shall see, this difference in design has profound consequence for the way the database is used. Reading to the database when a node is down. Imagine you have a database with 3 replicas, and one of the replicas is currently unavailable. Perhaps it is being rebooted to install a system update. In a leader-based configuration, if you want to continue processing writes, you may need to perform a failover, the handling nodes outage on page 156. On the other hand, in a leaderless configuration, failures do not exist. Figure 510 shows what happened. The client user 1, 2, 3, 4 send the write to all the 3 replicas in parallel, and the 2 available replicas accept the writes, but the unavailable replicas miss it. Let's say that it's insufficient for some Let's say that it's sufficient for 2 or 3 replicas to acknowledge the writes after user 1, 2, 3 had received 2 OK responses. We consider the writes to be successful. The client simply ignores the fact that one of the replicas misses the write. Now imagine that the unavailable nodes come back online and clients start reading from it. Any writes that happen while the node was down are missing from that node. Thus, if you read from that node, you may get stale, outdated values and responses. To resolve the problem, when a client reads from the database, it doesn't just send it a request to the one replica. Read requests are also sent to several nodes in parallel. The client may get different responses from different nodes. The up-to-date value from one node and the stale value from another. Version numbers are used to determine which value is newer. See detected concurrent write on page 184. Read, repair, and anti-entropy. The replication scheme should ensure that eventually all the data is copied to every replica. After an unavailable node comes back online, how does it catch up on the writes that it missed? 2 mechanisms are often used in Dynamo-style data store. Read repair. When a client makes a read from several nodes in parallel, it can detect any stale response. For example, in figure 510, user 2, 3, 4, 5 gets a version 6 value from a replica 3 and a version 7 from a replica 1 and 2. The client sees the replica 3 has a stale value and writes the newer value back to the replica. This approach works well for values that are frequently read. Anti-entropy process. In addition, some data stores have a background process that constantly looks for difference in the data between replicas and copy any missing data from one replica to another. Unlike the replication logs in leader-based replication, this anti-entropy process does not copy writes in any particular order, and there may be a significant delay before data is copied. Not all systems implement both of these. For example, Voldemort currently does not have any anti-entropy process. Note that without an anti-entropy process, values that are rarely read may be missing from some replica and thus have reduced durability, because read repair is only performed when a value is read by the application. Quorum for reading and writing. In the example of figure 510, we consider the write to be successful, even though it was only processed on 2 out of 3 replicas. What if only one of the 3 replicas accept the write? How far can we push this? If we know that every successful write is guaranteed to be present on at least 2 out of 3 replicas, that means at most 1 replica can be stale. Thus, if we read from the last 2 replicas, we can be sure that at least one of the 2 is up to date. If the third replica is down or slow to respond, reads can nevertheless continue returning an up-to-date value. More generally, if there are any n replicas, every write must be confirmed by the WB nodes to be considered successful, and we must query at least R nodes for each read. In our example, n equal 3, wb equal 2, r equal 2. As long as w plus r greater than n, we expect to get an up-to-date value when reading, because at least one of the r nodes we are reading from must be up to date. Read and writes that obey these R and W values are called quorum reads and writes. You can think of R and WB as the minimum number of both required for the reads or write to be valid. In Dynamo star databases, the parameters n, WB, and R are typically configured. A common choice is to make n an odd number, typically 3 or 5, and to set WB equal R equal n plus 1 divided by 2 rounded up. However, you can vary the number as you see fit. For example, a workload with few writes and many reads may benefit from setting W equal n and R equal 1. This may read faster, but has the disadvantage that just one failing node causes all database write to fail. There may be more than n nodes in the cluster, but in any given value is stored only on n nodes. This allows the database to be partitioned, supporting datasets that are larger than you can fit in one node. We will return to partitioning in Chapter 6. The quorum condition is WB plus R greater than n allows the system to tolerate unavailable nodes as follows. If WB is lower than n, we can see process write if a node is unavailable. If R lower than n, we can still process reads if a node is unavailable. With n equal 3, WB equal 2, and R equal 2, we can tolerate one unavailable node. With n equal 5, WB equal 3, and R equal 3, we can tolerate two unavailable nodes. This case is illustrated in figure 5.11. Normally, reads and writes are always sent to all n replicas in parallel. The parameters WB and R determines how many nodes we wait for. How many of the n nodes need to report to sex before we consider to read or write to be successful. If fewer than the required W, B, or R nodes are available, writes or reads return an error. A node could be unavailable for many reasons, because the node is down, crash, power down, due to an error executing the operation. Can't write because the disk is full, due to a network interruption between the clients and the nodes, or for any number of other reasons. We only care where the node returns a successful response and don't need to distinguish between different kinds of faults. Limitation of quorum consistency. If you have n replicas and you choose WB and R such that WB and R greater than n, you can generally expect every read to return the most recent value written for a key. This is the case because the set of nodes to which you're reading and the set of nodes from which you have read must overlap. This is among the nodes you read, there must be at least one node with the latest value. Often R and WB are chosen to be a majority, more than n divided by 2 of nodes, because that ensures WB plus R greater than n while still tolerating up to n divided by 2 nodes failures. But quorums are not necessarily majorities. It only matters that the set of nodes used by the read and write operations overlap in at least one node. Other quorum assignments are possible, which allows some flexibility in the design of distributed algorithm. You may also set WB and R to smaller number, so that WB and R lower and equal than n. For example, the quorum condition is not satisfied. In this case, read and writes will still be sent to n nodes, but a smaller number of successful responses is required for the operation to succeed. With a smaller WB and R, you are more likely to read step values, because it's more likely that your read didn't include the node with the latest value. On the upside, this configuration allows lower latency and higher availability. If there is a network interruption and many replicas become unreachable, there are higher chances that you can continue processing reads and writes. only after the number of reachable replicas fall below W or R, does the database become unavailable for writing or reading respectively. However, even with W, B, and plus R greater than N, there are likely to be edge cases where stale values are returned. This depends on the implementation, but possible scenarios include if a sloppy quorum is used, see sloppy quorums and hinted handoff on page 183, the WB writes may end up on different nodes than the error reads. So there is no longer a guarantee overlap between the R nodes and the W nodes. If two writes occur concurrently, it's not clear which one happened first. In this case, the only safe solution is to merge the concurrent writes. See handling writes conflict on page 175. If a winner is picked based on a timestamp, let's write wins, writes can be lost due to clock skew. We will return to this topic in detecting concurrent write on page 184. If a write happens concurrently with a read, the write may be reflected in only some of the replicas. In this case, it's undetermined, where the read returns the old or the new values. If a write succeeds on some replicas but fail on others, for example because the disks on some nodes are full and overall succeed on fewer than W replicas, it's not rolled back on the replicas where it succeeds. This means that if a write was reported as a failure, subsequent reads may or may not return the value from that write. If a node carrying a new value fails, and its data is restored from a replica carrying an old value, the number of replicas storing the new value may fall below WB, breaking the quorum condition. Even if everything is working correctly, there are edge cases in which you can get unlucky with the timing, as we shall see in linearizability and quorums on page 334. Thus, although quorums appear to guarantee that a re-return the latest write rate and value, in practice it is not simple. Dynamo style databases are generally optimized for use cases that can tolerate eventual consistency. The parameters WB and R allows you to adjust the probability of a stale value being read, but it's wise not to take them as absolute guarantees. In particular, you usually do not get the guarantees discussed in problems with replication lag on page 161. Reading your writes, monotic reads, and consistent prefix reads. So, the previously mentioned anomalies can occur in applications. A stronger guarantee generally requires transactions or consensus. We will return to this topic on Chapter 7 and Chapter 9. Monitoring stateliness. From an operational perspective, it is important to monitor whether your database are returning up-to-date results. Even if your application can't tolerate their reads, you need to be aware of the health of your replication. If it falls behind significantly, it should alert you so that you can investigate the causes. For example, a problem in the network or an overloaded node. For leaders-based replication, the database typically exposes metrics for the replication lag, which can feed into a monitoring system. This is possible because writes are applied to the leader and to follower in the same order, and each node has a position in the replication log. The number of writes it has applied locally. By subtracting a follower concurrent position from the leader's current position, you can measure the amount of replication lag. However, in systems with leaderless replication, there is no fixed order in which writes are applied, which makes monitoring more difficult. Moreover, if the database only uses read repair, not anti-entropy, there is no limit to how old value might be. If a value is only infrequently read, the value returned by a stale replica may be ancient. There has been some research on measuring replica stateliness in databases with leaderless replication and predicting the expected percentages of stale read depending on the parameter NW, B, and R. This is unfortunately not yet common practice, but it will be good to include staleness measurement in the standard set of metrics for databases. Eventual consistency is a deliberated back guarantee, but for operability, it is important to be able to quantify eventual. Sloppy quorums and hinted handoff. Databases with appropriately configured quorums can tolerate the failures of individual nodes without the need for failover. They can also tolerate individual nodes going slow because requests don't have to wait for all end nodes to respond. They can return when WB nodes or R nodes have responded. This characteristic made databases with leaderless replication appealing for use cases that require high availability and low latency and that can tolerate occasional state reads. However, quorums, as described so far, are not as fault-tolerant as they could be. A network interruption can easily cut off a client for a large number of database nodes, although those nodes are alive, and other clients may be able to connect to them. To a client that is cut off from database node, they may as well be dead. In this situation, it's likely that fewer than WB and R reachable nodes remain, so the client can no longer reach a quorum. In a large cluster, with significantly more than n nodes, it's likely that the clients can connect to some databases node during the network interruption, just not to the nodes that it needs to assemble a quorum for a particular value. In that case, database designers face a trade-off. Is it better to return error to all requests for which we cannot reach a quorum of WB or R nodes? Or should we accept writes anyway and write them to some nodes that are reachable but are not among the end nodes on which the value usually lives? The latter is known as a sloppy quorum. Writes and reads still require WB and R successful responses, but those may include nodes that are not among the designated end homes node for a value. By analogy, if you lock yourself out of your house, you may knock on the neighbor door and ask whether you may stay on their couch temporarily. Once the network interruption is fixed, any writes that one node temporarily accepts on behalf of another node are sent to the appropriate home nodes. This is called hinted handoff. Once you find the key to your house again, your neighbor politely asks you to get off the couch and go home. Sloppy quorums are particularly useful for increasing writes availability, as long as any WB nodes are available. The databases can accept writes. However, this means that even when WB and R greater than n, you cannot be sure to read the latest value for a key, because the latest value may have been temporarily written to some nodes outside of n. Thus, a sloppy quorum actually is not a quorum at all in the traditional sense. It's only an assurance of durability, namely that the data is stored on WB nodes somewhere. There is no guarantee that the read of R nodes will see it under the hinted handoff has completed. Sloppy quorums are optional in all common Dynamo implementation. In React, they are enabled by default, and in Cassandra and Voldemort, they are disabled by default. Multi-data centers operations. We previously discussed cross-data center replication as a use case for multi-leader replication. See multi-leader replication on page 168. Leaderless replication is also suitable for multi-data centers operation since it's designated to tolerate conflicts, concurrent write, network interruption, and latency spikes. Cassandra and Voldemort implement the multi-data center support within the normal leaderless model, the number of replicas, and include nodes in all data centers. And in the configuration, you can specify how many of the n replicas you want to have in each data center. Each write from a client is sent to all replicas, regardless of data center. But the client usually only waits for acknowledgement from a quorum node within its local data center so that it's unaffected by delays and interruption on the cross data center link. The higher latency writes to other data centers are often configured to happen asynchronously, although there is some flexibility in the configuration. React keeps all communication between clients and databases not local to one data center. So N describes the number of replicas with one data center. Cross data center replication between databases clusters happens asynchronously in the background in a style that is similar to multi-leader replication. Detecting concurrent write. Dynamo style databases allow several clients to concurrently write to the same key, which means that conflict will occur even if a strict quorum are used. The situation is similar to multi-leader replication. See handle write conflict on page 171. Although in Dynamo style databases, conflict can also arise during read repair, or hinted handoff. The problem is that events may arrive in a different order at different nodes due to variables, network delays, and partial failures. For example, figure 512 showed two clients A and B simultaneously reading to a key X in a 3-node data store. Node 1 received the write from A but never received the write from B due to a transient outage. Node 2 first received the write from A, then the write from B. Node 3 first received the write from B and then the write from A. In each node, simply overwrote the value for a key whenever it received a write request from a client. The nodes will become permanently inconsistent, as shown by the final GET request on figure 512. Node 2 thinks that the final value of X is B, whereas the other nodes think that the value is A. In order to become eventually consistent, the replicas should converge toward the same value. How do they do that? We might hope that replicated databases will handle this automatically, but unfortunately, most implementations are quite poorly. If you want to avoid losing data, you, the application developer, need to know a lot about the internal of your database conflict handling. We briefly touched on some technique for complete resolution in handle write conflict on page 171. Before we wrap up this chapter, let's expose the issue in a bit more detail. Last write wins, discarding concurrent writes. One approach for achieving eventual convergence is to declare that each replica needs only store the most recent value and allow values to be overridden and discarded. Then, as long as we have some way of unambiguous determining which write is more recent, and everywhere is eventually copied to every replica, the replicas will eventually converge to the same value. As indicated in the quotes around recent, this idea is actually quite misleading. In this example figure 512, neither client knew about the other one when it sent its write request to the database node, so it's not clear which one happened first. In fact, it doesn't really make sense to say that either happened first. We say the writes are concurrent, so the order is undefined. Even though the writes don't have a natural ordering, we can force an arbitrary order on them. For example, we can attach a timestamp to each write, pick the biggest timestamp of the most recent, and discard any writes with an early timestamp. This complete resolution algorithm, called last write wins (LWBWB), is the only supported complete resolution method in Cassandra, and an optional feature in Riot. LWBWB achieved the goal of eventually convergence, but at the cost of durability. If there are several concurrent writes to the same key, even if they were all reported as successful to the client because they were written to WB replicas, only one of the writes will survive and the other will be silently discarded. Moreover, LWBWB may even drop writes that are not concurrent, as we shall discuss in timestamp for ordering events on page 291. There are some situations such as catching in which lost writes are perhaps acceptable. If losing data is not acceptable, LWWB is a poor choice for complete resolution. The only safe way of using a database with LWWB is to ensure that a key is only written once and thereafter treated as immutable. Thus, avoiding any concurrent updates to the same key. For example, a recommended way of using Cassandra is to use an UUID as the key, thus giving each write operation a unique key. That happens before relationship and concurrency. How do we decide whether two operations are concurrent or not? To develop an intuition, let's look at some examples. In figure 5.9, the two writes are not concurrent. As insert happens before, B increments because the value increments by B in the value insert by A. In other words, B operation builds upon an operation, so B operation will have happened later. We also say that B is causally dependent on A. On the other hand, the two writes on figure 5.12 are concurrent. When each client starts the operation, it does not know that another client is also performing an operation on the same key. Thus, there is no causal dependency between the operation. An operation happened before another operation B if B knows about A, or depends on A, or builds upon A in some way. Whether one operation happens before another operation is the key to defining what concurrency means. In fact, we can simply say that two operations are concurrent if neither happened before the other. Neither knows about the other. Thus, whenever you have two operations A and B, there are three possibilities. Either A happened before B, or B happened before A, or A and B are concurrent. What we need is an algorithm to tell us whether two operations are concurrent or not. If one operation happened before another, the later operation should override the earlier operation, but if the operations are concurrent, we have a conflict that needs to be resolved. Concurrency, time, and relativity. It may seem that two operations should be called concurrent if they occur at the same time, but in fact, it's not important where they literally overlap in time. Because of the problem with clock in distributed system, it's actually quite difficult to tell whether two things happen at exactly the same time, and each will be discussed in more detail in chapter 8. For defining concurrently, exact time doesn't matter. We simply call two operations concurrent if they are both unaware of each other, regardless of the physical time at which they occur. People sometimes make a connection between this principle and the special theory of relativity in physics, which introduced the idea that information cannot travel faster than the speed of light. Consequently, two events that occur some distance apart cannot possibly affect each other if the time between the events is shorter than the time it takes light to travel the distance between them. In computer systems, two operations might be concurrent, even though the speed of light would in principle have allowed one operation to after the other. For example, if the network was slow or interrupted at the time, two operations can occur sometime apart and still be concurrent, because the network problems prevented one operation from being able to know about the other. Capturing the happens before relationship. Let's look at an algorithm that determines whether two operations are concurrent or whether one happened before another. To keep things simple, let's start with a database that has only one replica. Once we have worked out how to do this on a single replica, we can generalize the approach to a leaderless database with multiple replicas. Figure 513 shows two clients concurrently adding items to the same shopping cart. If that example strikes you as too in name, imagine instead two air traffic controllers concurrently adding aircraft to the sector they are tracking. Initially, the cart is empty between them. The client made 5 writes to the database. Client 1 adds milk to the cart. This is the first write to that key. So the server successfully stored it and assigned it version 1. The server also echoes the value back to the client along with the version number. Client 2 adds X to the cart, knowing that client 1 concurrently added milk. Client 2 though that is an X were the only item in the cart. The serves assign version 2 to the right and store X and milk as two separated values. If then return both values to the client along with the version number of 2. Client 1 obviously to client 2 writes, want to add flavor to the cart, so it thinks the current cart content should be milk flour. He sent this value to the server along with the version number 1 that the server gave client 1 previously. The server can tell from the version number that the writes of milk flow supersedes the prior values of milk, but that is concurrently with X. Thus, the server assigns version 3 to milk flour, overwrites the version 1 values, but keeping the version 2 values and returning both remaining values to the client. Meanwhile, client 2 wants to add ham to the cart. Unaware that client 1 just added 4, client 2 received the two values, milk and eggs, from the server in the latest response. So the client now merges those values and add ham to form a new value, eggs, milk, ham. It sends that value to the server along with the previous version number 2. The server detects that version 2 overwrites, but it's concurrently with milk and flour. So the two remaining values are milk, flour with version 3 and eggs with milk ham with version 4. Finally, client 1 wants to add bacon. It previously received milk, flour, and eggs from the server at version 3, so it merged those at bacon and sends the final value, milk, flour, eggs, bacon, to the server along with the version number 3. This overwrites milk, flour. Note that x was already overridden in the late step, but it's concurrent with x milk ham, so the server keeps those two concurrent values. The data flow between the operation in figure 513 is illustrated graphically in figure 514. The arrows indicate which operation happened before, which other operation, in the sense that the later operation knew about or depends on the earlier one. In this example, the clients are never fully up to date with the data on the server, since there is always another operation going on concurrently, but all versions of the value do get overridden eventually and no writes are lost. Note that the server can determine whether two operations are concurrently by looking at the version number. It does not need to interpret the value itself, so the value could be any data structure. The algorithm works as follows. The server maintains a version number for every key, increments the version number every time that key is written, and stores the new version number along with the value written. When a client reads a key, the server returns all values that have not been overridden, as well as the latest version number. A client must read a key before writing. When a client writes a key, it must include the version number from the prior read, and it must merge together all values that it received in the prior read. The response from a write request can be like a read, returning all current values, which allow us to change several writes, like in the shopping cart example. When the server receives a write with a particular version number, it can overwrite all values with that version number or below, since it knows that they have been merged into the new value. But it must keep all values with a higher version number, because those values are concurrently with the incoming write. When a write includes the version number from a prior read, that tells us which previous state the write is based on. If you make a write without including a version number, it is concurrent with all other writes, so it will not overwrite anything. It will just be returned as one of the values on subsequent reads. Merging concurrently written values. This algorithm ensures that no data is silently dropped, but it unfortunately requires that the client do some extra work. If several operations happen concurrently, clients have to clean up afterward by merging the concurrently written values. Red called these concurrent value siblings. Merging siblings value is essentially the same problem as conflict resolution in multi-leader replication, which we discussed previously. See handle write conflict on page 171. A simple approach is to just pick on one of the values based on the version number of timestamp. Last write wins, but that implies losing data, so you may need to do something more intelligent in application code. With the example of a shopping cart, a reasonable approach to merging the siblings is to just take the union. In figure 514, the two final siblings are milk, flour, eggs, and bacon. And eggs, milk, ham. Note that milk and eggs appear in both, even though they were each only written once. The merged value might be something like milk, flour, eggs, bacon, ham, without duplicates. However, if you want to allow people to also remove things from their cart and not just add things, then taking the union of siblings may not yield the right result. If you merge two sibling cards and an item has been removed in only one of them, then the removed item will reappear in the union of siblings. To prevent this problem, an item cannot simply be deleted from databases when it's removed. Instead of the system will leave a marker with the appropriate version number to indicate that the item has been removed when merging siblings. Such a deletion marker is known as tombstone. We previously saw tombstone in the context of log companion in hash index on page 72. As emerging siblings and application code incomplete and error prone, there are some efforts to design data structure that can perform this merging automatically. It is discussed in automatic conflict resolution on page 174. For example, write data type support users a family of data structure called S called CRDT that can automatically merge siblings in sensitive ways, including preserving deletions. Version vectors. The example in figure 513 uses only a single replica. How does the algorithm change when there are multiple replicas but no leaders? Figure 513 uses a single version number to capture dependencies between operations, but that is not sufficient when there are multiple replicas accepting writes concurrently. Instead, we need to use a version number per replica, as well as per key. Each replica increment is shown version number when processed a write, and also keeps track of the version number it has seen from each of the other replicas. This information indicates which values to overwrite and which value to keep as siblings. The collection of version numbers from all replicas is called version vector. A few variants of this idea are in use, but the most interesting is probably the daughter version vector, which is used in Riot. We won't go into the details, but the way it works is quite similar to what we saw in our card example. Like the version number in figure 513, version vectors are sent from a database replica to clients when values are read and need to be sent back to the database when a value is subsequently written. Ryan encodes a version vector as a string that is called casual context. The version vectors allow the database to distinguish between overwrites and concurrent writes. Also, like in the single replica example, the application may need to merge siblings. The version vector structure ensures that it is safe to read from one replica and subsequently writes back to another replica. Doing so may result in siblings being created, but no data is lost as long as siblings are merged correctly. Version vectors and vector clocks. A version vector is something also called a vector clock, even though they are not quite the same. The difference is subtle. Please see the difference for details. In brief, when comparing the state of replica, version vectors are the right data structure to use. Summary. In this chapter, we look at the issues of replications. Replication can serve several purposes. High availability, keeping the system running even when one machine or several machines or one entire data centers go down. Disconnected operation, allowing an application to continue working when there is a network interruption. Latency, placing data hierarchically close to users so that user can interact with it faster. Scalability, being able to handle a high volume of reads than a single machine could handle by performing reads on replicas. Despite being a simple goal, keeping a copy of the same data on several machine replication turns out to be a remarkably tricky problem. It requires careful thinking about concurrency and about all the things that can go wrong and dealing with the consequences of those faults. At a minimum, we need to deal with unavailable nodes and network interruptions, and that's not even considered the more insidious kind of faults, such as silent data corruption due to software bug. We discussed three main approaches to replication: single leader replications, clients send all write to a single node, the leader, which send a stream of data changes event up to the other replica's followers. Reads can be performed on any replica, but reads from follower might be stale. Multi-leader replications. Clients send each write to one of several leader nodes, any of which can accept writes. The leader sends streams of data changes even to each other and to any follower nodes. Leaderless replication. Clients send each write to several nodes and read from several nodes in parallel in order to detect and correct nodes with stale data. Each approach has advantages and disadvantages. Single leader replication is popular because it is fairly easy to understand and there is no conflict resolution to worry about. Multi-leader and leaderless replication can be more robust in the presence of faulty nodes, network interruptions, and latency spikes, at the cost of being harder to reason about and providing only very with consistency guarantees. Replication can be synchronous or asynchronous, which has a profound effect on the system behavior when there is a fault. Although asynchronous replication can be fast, when the system is running smoothly, it is important to figure out what happened. When replication lag increases and servers fail, if a leader fails and you promote an asynchronous update follower to be the new leader, recently committed data may be lost. We look at some strange effects that can be caused by replication lags, and we discuss a few consistent models which are helpful for deciding how an application should behave under replication lags. Read after write consistency. Users should always see data that they submitted themselves. Monotonic reads. After users have seen the data at one point in time, they shouldn't later see the data from some early point in time. Consistent prefix reads. Users should see the data in a state that makes casual sense. For example, seeing a question and its reply on the correct order. Finally, we discussed the concurrency issue that are inherent in multi-leaders and leaderless replication approaches. Because they allow multiple writes to happen concurrently, conflicts may occur. We examine an algorithm that a database might use to determine whether one operation happened before another, or whether they happen concurrently. We also touched one method for resolving conflict by merging together concurrent updates. In the next chapter, we will continue looking at data that is distributed across multiple machines through the counterpart of replication, splitting a large dataset into partitions.